So let's take a moment to talk about some pre-lab concepts. Specifically, we're going to talk about error, what it is and what it isn't. First thing I want you to know about error is that it is not a mistake. Repeat, it is not a mistake. All it tells us is how much do you trust your number, how far to one direction or another can. So the first thing we need to know is there are a couple types of error, and I'm just going to refer to these as uncertainty, because that's kind of what we're looking for. This just tells us the range of measurements we could get. So first, we're going to talk about systematic. This is uncertainty due to a measurement setup. So if we have a meter stick, most of the time they'll be made of wood. And on a humid day, what's wood do? It expands. So they're hard to find. There are problems in the setup itself. The good news is they're always the same. So if you knew your meter stick grew 2%, you just add 2%. The other type, which is the one we're going to account for the most, is this called random error, or plus minus, which is a range of values that people will get. If we ask your partner and you to measure the same thing, odds are you're going to get different numbers. So what we need to do is we need to find a way to fix this, or at least to account for it. And the way we're going to account for this are by getting more values. So let's take a moment and talk about the parts of an answer. There are two parts to every answer. First is your average. This represents the most probable value that you're going to get. The most probable value. This is the 4 out of 5 dentists prefer Trident, or whatever it is. So it's just, where your average is. And then you have your uncertainty. This tells you your range. And let's figure out how we calculate this range. So what we have here is a big set of data. And we have less than 10 measurements. And you can see we have 1, 2, 3, 4, 5, 6 measurements, which is less than 10. Go math. And we want to use maximum deviation. So the first thing, if we were to report this answer, is we would find our average, plus or minus, your max. I'm just going to write deviation from average. From the average. So if we average this, the average of these numbers comes out to be 7.0 plus or minus, well, let's see which one's farthest from the average. And if the average is 7.0, looks like it's this one right here, which is 0.4, so that would be 0.4. So I need a decimal point there. 7.0. So when you're reporting this number, you would report it as 7 plus or minus 0.4. Now, if you have more than 10 measurements, you use standard deviation. Now, because this is a very big pain, you're only going to have to mess with this in your very first lab on measurements, and I'm going to show you how to do it, but I'm only going to use 6. So, to suspend belief, pretend we've got a little more value points, and we'll show you how to use this formula. First thing I want you to notice, this is summation. This means you are going to add the values of xi minus x average squared. So xi would just be 0.1, 2, 3, 4, 5, all the way up to n points. Big n points. So if I were to do this, this would be 7.2, minus 7 squared plus 7.4 minus 7 squared plus all over. I had 6 measurements, so this would be 6 minus 1. Again, only use it when you have more than 10 measurements, equals your standard deviation. If I carry out that math, I'll get something in the neighborhood of like 0.3, which is smaller than 0.4 that we got before. That's because this is a better statistical method. So hopefully you get better data using statistics and more measurements. One thing that I forgot to mention a little earlier, this standard deviation that we're using is standard deviation of a sample. So if you're using Excel or something like that, this would be represented by stdev.s function. There's two. There's population and then there's sample. We use the sample version in our physics class. This is something I'm going to mention. We will use it in the free fall lab. Sometimes when you measure a quantity, you are looking for the mean, or the average. Like we will measure the acceleration due to gravity in lab 2. You are finding the average acceleration of gravity, And if you take more measurements, your value should get better. So this right here is what we call standard deviation of the mean, which divides by this other factor of square root of n. If you take more measurements, your results should be more accurate. Those of you who take modern will actually see how this is derived in our error analysis course, but for now, just kind of say more measurements, better numbers. So now the moment I know you've all been waiting for, getting significant figures. And first off, we should kind of talk about what a significant figure is. It's a figure that is significant. I should probably tell you a little more than that. This tells you how important the accuracy of your measurements, how important each digit is. So this is the accuracy of your measurements. Now we do it a little bit different here. In physics, your plus or minus is determined by this uncertainty. So let's look. I've got some uncertainty on numbers. We're adding. So what do these add together? Well, remember, this right here is the most probable value. So if I add the most probable value, which would be adding the averages, I'm going to come up with 6.0. If I'm adding, the biggest number I could get is, well, if this was actually 2.5, and if this was 4, well, that would be 6.5. Which you get just by adding those numbers. So 0.5. So if you add or subtract, you add absolute uncertainties. Multiplying or dividing is a little bit trickier, because if I did this right, I would have 6.0 plus or minus. If I multiply this, I would just get 0.006, which means my numbers got better by adding and multiplying worse things. You will never get better by adding horrible numbers. So this is why we have to add the relative percents. So if we look at this, plus some percent. So to get this percent, let's look at this. Let's look at this first number. Okay, 0.2 out of 2 is 10%. Likewise, 0.3 over 3 equals 10%. It's like I chose those numbers because they were easy. That's exactly why I chose them, is 20%. So now we have 6.0 plus or minus 20%, which is equal to 6.0 plus or minus 1.2. So when we're doing it this way, you have to add the percents, which is to say, whenever you multiply or divide, find the percent that the uncertainty is of one number, find the percent it is of the second number, add those percents together, and come up with your total error, and convert back to a number. And this would be the moment you've all been waiting for. How do we know how many significant figures we have? Simple. If the first number is 1, keep 2. This is in the uncertainty, by the way. In the uncertainty. So the reasoning behind this is that let's say you have plus or minus 0.13. This 3 right here is 30% of this first number, which is a big fraction of your error. If you have plus or minus let's say 5, then this 3, not as big, doesn't really matter. So when we're in this, we're trying to encompass the major parts of our uncertainty. The other rule is once you've determined how many digits you're keeping, so the first number is not 1, so you're just going to keep one place, then we see that this is in the ones column. So your uncertainty goes to the same column here. So if this is 7, this goes to the ones column, the number it's modifying also goes to the ones column. So this would be 7 plus or minus 3, which isn't really great numbers. Let's try this second one. The first number is 1, so we're going to keep 2 spots. That goes to the ones column. This goes to the ones column. So you get 1305 plus or minus 12. Oh, wait, it's not 1 again. So we're going to keep 2 spots. So this is plus or minus 0.18 because we're rounding. Standard rules apply. Goes to the hundredths place. Goes to the hundredths place. So you get 158.62. That was my son. He is also learning about uncertainty. And then our final example. This goes out to, oh wait, first number is not 1, so we're only going to keep 1 spot. which goes out to the hundredths place, which means this goes to the hundredths. So all these other digits, not significant. We can't report that accuracy. So 2.32 plus minus 0.5. So I hope that makes sense. Just to recap the major rules. Sig figs are determined by your uncertainty. If it's plus or minus, you add your numbers. If you multiply or divide, you add your percents. And that's it. So if you have any questions as you go through the lab, please ask myself or your lab instructor, or me if I am your lab instructor, and we will help you out, because that's what we're here for. So I'll talk to you later. I'll see you in lab. Thanks.